All right, everyone. Thanks for joining for our last session today before our 2-day recap. Mr. John White will be on to wrap up the summit for us after us, so make sure you tune in for that. Before we get started, big shout out to the participating sponsors and partners. So Lodo Cloud, Geico, NetSource One, Nutanix, Ampere, Shape Blue, and the Cube. Thank you so much for participating in our chats here. Today, we are going to be going over the future of compute. So AI compute from the cloud to the edge. So really at the core of our talk, we're going to be talking a lot about the pace of innovation, kind of the demands that we're seeing from a performance standpoint, from a scalability standpoint, and a sustainability standpoint, right? So from a power standpoint, and just a space standpoint that kind of AI and edge is starting to have on the industry. So whether you're powering complex AI inference models in the cloud or trying to enable real-time decision making, as close to the edge as possible, the future of compute is being shaped now, today, kind of right in front of our eyes. So we're going to dive into how technology is enabling that high efficiency compute across kind of all of these environments and what it means for industries that are working a lot in the AI, ML, IoT, and cloud native workloads. We'll talk over some use cases, some metrics, and some architectural strategies. So I'm joined today by Sean Varley from Ampere. He's the lead evangelist. He's got an awesome beard, which is a very cool thing and very needed in the industry. Adds credibility, right? So we're going to get started here. I'm going to be running through a slideshow that Sean put together for us ahead of time. Let's see. All right, Sean, why don't you go ahead and take it away? Talk to us about forming a cloud native foundation for AI compute.
Thank you, Dob, and thank you for having me. I'm really pleased to be here with you all today. So I thought, with that introduction, we would just kind of set some basics, some background about kind of what we're talking about. When we talk about AI compute, when we talk about cloud native computing, and when we talk about sort of alternative architectures for sustainable computing. And what you're seeing here is really kind of the fundamental difference in a nutshell between an x86 architecture and a cloud native architecture, which pretty much all of the cloud native architectures are similarly structured. When Ampere, which is about 8 years old now, was first formed, and we were kind of novel in this thing, but now we're joined by many others in doing this kind of a thing. So on the left-hand side, what you see is a typical core for an x86 processor, of course, has 2 threads. And those tasks can get scheduled on either thread, and they're basically called virtual CPUs. But they have their own set of registers, but then after that, then they share everything in the pipeline. Now, what you have on the right-hand side is a cloud-native approach, where you've got essentially cores that are single-threaded. They share nothing. And so what you see here is essentially the reservation of resources for all processes that are scheduled on the processor. In addition to that, you can get into many other details, which I won't go and digress into today, but essentially that's a fundamental difference. Because why? In cloud native architecture, you are essentially a scale out architecture where processes are scheduled on threads or vCPUs. This is how the cloud works in general. And then those processes continue to completion. And if they're interrupted by, say, hyperthreading, then all of a sudden you get a lot of unpredictability and all of these sorts of things, which we'll talk about in a moment. And that really kind of messes up what we call cloud native code because it's unreliable, it's unpredictable, and generally there's a lot of sort of repercussions, shall we say, to this type of an architecture, and maybe some unintended consequences to those, and we'll talk a little bit more about that. But essentially why we did this was for performance, efficiency, and scalability. And Davin, will you please advance the slide? Thank you. All right, so what do you get out of an architecture like this, right? First of all, a scale-out architecture like this, especially if it's designed the way Ampere has designed processors, is to really, really get a tight core. In other words, small in die area, small in power consumption, and you get many of those cores in one processor. Our processors are up to 192 cores, and that really kind of changes the game when you're talking about a cloud native performance profile, which is also characterized by these characteristics: predictable low latency. The lower left is a micro shot of cloud native code base, in this case Redis, operating. And what you see here is in the gray lines an x86 processor returning the requests for completion out of Redis. And you can see that they bounce around, right? The red line is the Ampere processor, of course, and you can see that it's very, very consistent across every run. Now that gives you one part of the profile. The other thing about scheduling things on hyper-threaded cores is the behavior you get in the middle. In the middle, when you schedule something on a core, the throughput that you were enjoying with the first thread is interrupted by the second thread. So you get these dropouts, right? That's partially contributing to the thing on the left, but it's also making the overall throughput of an entire set of applications very, very unpredictable. And then finally, what you get, and this is what maybe one of the unintended consequences I was referring to earlier, is in an x86 processor, when you're trying to schedule a load, you typically don't schedule loads much greater than about 50% utilization. Why is that? Because of those threads. Again, threads are false capacity. You don't actually have all of the resources underneath that thread to complete an action, so to speak, on the same SLA or service level agreement as all the other threads. And so what happens with that is after 50% utilization, everything tapers off. And so that's just trained the industry to operate processors at about 50% utilization. And utilization turns out to be one of the greatest things that we can do to become more sustainable, completely use all of the resources in a processor. So you get this linear scaling effect in the cloud native architecture, because essentially every time you schedule something, you're scheduling a new core. And if you're at 90% utilization, that just means you're using 90% of the cores in the processor.
So
Okay, so
Sean,
this one way. Yeah, go ahead.
real quick. Yep, real quick. So what are the implications? So we see the graphs. We're talking about latency, throughput, and scaling. So
Mm-hmm.
for those that are trying to run some of the newer automation AI ML type workloads on x86, right? What are the
Mm-hmm.
ramifications of running those on x86, right? You talked a little bit about, effectively we're training ourselves to run at 50% capacity. I'm assuming there's cost ramifications, right? There's a lot more hardware needed to get to some of the performance that you would need in x86 versus an ARM
Yes.
type architecture. Can you go over that?
Yeah, absolutely. And thanks for the question, because I think this is a really, really salient piece. And actually, if you go back a slide,
Yep.
one of the things I'll point out, if you can, one of the things I'll point out is that when you're talking about workloads like AI or any other computationally intensive workload, say it's transcoding or something like that, essentially you're utilizing that AVX or now AMX vector unit, right, which is the very bottom of this diagram. One of the things that is sort of maybe a dirty little secret is that only that particular resource can only actually sustain one thread. So hyperthreading is useful or valuable in these types of workloads, and so people turn it off often, or they just don't schedule them, right? By keeping the utilization low, like we were talking about earlier. On the right hand side, you see you've got vector units dedicated to each core. And so those vector units, which are super important for computing AI, get dedicated to each individual task. Now we can go and advance again forward to the next slide, but the AI industry is a modern industry, right? It hasn't been around that long. So essentially the software has already been programmed in an age where cloud native, serverless, microservices are the norm. And so they're inherently built scale out. That means they're scheduled typically on containers and utilizing some kind of an elastic service like Kubernetes, to kind of be able to dynamically manage the workload of the AI users, the actual queries and things like that. So those things get scheduled on cores, and that basically is the way that we address kind of AI computing as opposed to x86. Now we can get into the capabilities of vector units and matrix math and things like that, but I'm going to save that for a further slide because I want to set some context up before we do that.
Yep, makes sense. Thank you.
Okay, so really quickly, on Ampere, we've essentially, as I said, we're an 8-year-old company. We've essentially produced 7 chips in that 8-year span, and about 2 per generation, as you see here. We have 3 generations out now. They're all high core count processors. We basically scale now from 32 to 192. And the older processors are all DDR4 Gen 4, and the newer processors are DDR5 Gen 5. Now, we took a different approach to the x86 industry once again by essentially, we don't have a lot of overlap in our roadmap, meaning we don't replace our parts the same way that the x86 industry does. Means they got a long life. And so the Ultra products now are really being utilized at the edge. And we'll talk about the edge in just a moment. The Ampere One products are now kind of that mainstream compute product. These are actually optimized in 2 flavors, an 8-channel DDR5 flavor and a 12-channel. The only difference, essentially. Why did we make this choice? Because the extra 4 channels are a lot of power, and they're only useful for about 85% of the modern workloads. Sorry, the 85% of the modern workloads cannot use the extra memory bandwidth. And so we chose not to penalize the industry by having all that extra power for a lot of the workloads that don't need it. But it turns out that one workload in particular really needs this extra memory bandwidth, and that's the AI, right? Especially Gen AI, which will basically consume all the memory bandwidth that you can throw at it. So the Ampere 1M processor on the far right of this chart is optimized essentially for that Gen AI and AI compute workload. And then the middle one, Ampere 1, really kind of optimized for traditional AI inference along with volume cloud computing environments. Now, we, of course, have been always on a sustainable computing path. And so we've started to define metrics, which we'll talk a little bit more in the next slides. First metric we'll talk about is really performance per rack. Next slide. Oh, actually, this is so we'll get to the performance per rack in the next slide, but the edge to cloud markets, right? All of those products I was just talking about kind of optimize from edge all the way into the cloud and the neo cloud. These are just some of the market segments that are served by this. And the point I'd really like to make here is that AI is going to be across all of these segments. It's not confined to data center, especially not confined to hyperscale data center or the neo clouds. And this is because AI is going to get actually implemented closer to people, and people are, of course, at the edge. And so that is going to be something that really challenges the current paradigms around AI, especially the paradigm that it's going to take a lot of horsepower and a lot of actual electricity to actually implement AI. While some of those notions are true, it's not all true that you need to do this kind of, sort of deep rack level implementation for all forms of AI. And so AI will kind of be utilized across all of these segments. The point of this particular slide is to say, look, variable core count matters in that type of arithmetic, because essentially what you can do is right size your computing for whatever application, whether it's at the edge or in the kind of hyperscale data center, for any of these types of markets that are sitting here on this slide.
Yeah, and you and I talked about that a little bit, right? Within AI, there's effectively multiple use cases, right? So whether or not you're pushing things to the edge for inference, post post learning for faster querying and just pushing closer to the edge in general, right? So if you're doing anything with AI from an IoT standpoint or sensors in a data center or something like that, you're going to want those workloads as close to humans as possible, as close to the work getting actually done.
Absolutely. Yep. Yeah, that's going to be super important. And of course, the closer to the edge you get, the more power constrained you get, typically, right? Even into smaller form factors, battery operation, all of these sorts of things can become a factor. And so this is where getting lean, and also designing for the use case, whatever the use case is. And if it's got, a heavy amount of AI in it, then you're going to want to do some modifications and optimizations that we'll get into in just a moment. Before we get there, let's talk about performance per rack, because this is a fundamental metric. We kind of pioneered this particular metric, and now a lot of the industry is really kind of picking up on it. Essentially, what it means is you're given a power budget, and a rack is inherently power limited. It's got a budget, and typically, the racks out there that you'll find in legacy data centers, in other words, data centers that haven't been refitted or have our new build, then you're going to see a budget between probably 10 kilowatts and 16 kilowatts, somewhere in that range. Maybe sometimes you'll get up into the 20s, but this is typically a budget that's fixed, and so you've got a certain amount of space, and you can put a certain amount of equipment within that space, and so this is a measure of compute inside of the rack. And essentially here you're seeing a comparison on some of the cloud native workloads. And also you're seeing at the very end there one actual AI workload where the current kind of volume compute architecture, our Ampere 1 architecture, is shown here in the red bars, as having anywhere from, say, about 30 to almost 90% better performance per rack, meaning that we're able to pack a lot more practical computing into that space and power envelope.
Yeah. And what we're seeing in the economy, the environment, and the industry right now, I talked about this before. Space and power is the name of the game right now, right? I think
Yep,
vacancy is at as an all-time low from a data center perspective right now. So certainly much more than just AI and performance and the technology around AI is like, how do you do that in a way that is economical, right? Which is kind of what we're talking about here.
exactly, exactly. And I think that this is going to go very well with this next slide, Davin, because kind of what you're talking about is that there's a lot of strategies right now to be able to kind of move that compute closer to people. We're seeing a lot of novel approaches to building data centers. We're seeing them in containers. We're seeing them on small pads, that are in, a lot more locations, tier two, tier three, even smaller cities and things like that. So that's one approach that I see actually being taken. And I think we've talked about this before. Maybe we can talk about it some more later. But there's other factors that are also really kind of driving a lot of this trend. And so in AI, because of sort of this gold rush, if you will, to get to a certain amount of infrastructure that can serve the demand for inference, as inference really takes hold of this particular workload, you're seeing a lot of concerns, right? You're seeing concerns around sovereignty. You're seeing concerns around data security. You're seeing a lot of concerns about economics, and of course, power as part of that economics. And you're seeing a lot of, man, I can't actually utilize all that GPU infrastructure very realistically, right? Utilization becomes a huge problem. And if you're leaving costly infrastructure like GPUs idle, then the money's just flying out the window. So right sizing for task is huge. And then of course we talked about the distribution for events and people. These are some of the top trends in the industry right now, along with another trend that we'll get into a little bit, what's called agentic AI. But we'll talk about that in the next slide. So I like to start out when we talk about AI with models. One of the things that happened, what was it, 4 or 5 years ago now? Maybe it wasn't even that long. 4 years ago was Gen AI hit the scene. And probably the biggest thing that was different from traditional machine learning and traditional AI models was Gen AI had a lot more parameters. And so what's kind of started to shake out now, 3 to 4 years later, is a model that looks kind of like this. On the right-hand side of this chart, you have really, really large models, right? Models that are north of 100 billion parameters, 500 billion, trillion parameters. ChatGPT is over a trillion parameters. These types of models, foundational models, are very expensive to run. The computational cost and the memory requirements, both for being able to run these models, is on an exponential curve. That's what you see there in that black line. And so we'll call those models basically anything sort of north of 30 to 50 billion parameters as large language models. Okay. These actually do require GPUs, or now what we call domain specific accelerators, or kind of purpose built accelerators for doing typically vector and matrix math. Um, and those things, are the domain, the rarefied domain of those types of architectures. What you see on the left-hand side of this chart is the smaller models. And there is an acronym now for it. It's called the Small Language Model, or SLM. And those models are very easily run in a lot less power and a lot less memory and a lot less computational horsepower. So those kinds of models are a lot cheaper to run, a lot more economical. And so what you see with agentic AI and many of these or other paradigms like multimodal, like a mixture of experts, a lot of these types of buzzwords you're hearing in the industry, is this migration of models to the lower end of this chart, right? You're seeing these small language models, which, by the way, you're not going to pay a penalty in accuracy for, because the small language models are typically trained on a very limited set of data, a vertical set of data. So they become experts. They become experts in one area. And so the accuracy actually goes up, paradoxically, with this kind of mixture of experts or smaller language modeling. And I think this is kind of intuitive, right? If you're asking a foundational model, it has to know everything from Shakespeare to medical imaging. And if you're asking an expert model, it only knows about one thing. And so these sorts of optimizations are sort of intuitive. As we start to build in reasoning and all these other things into AI modeling, this paradigm will continue to shift to the left. And so you'll see is a lot of models in this lower range.
And a lot of models in general shrinking, right?
Yep,
Yeah.
exactly. Yep. So here is the problem. Obviously, AI is too expensive. We talked about big racks of GPUs, their underutilization, and all these sorts of things. That's because a rack full of GPUs is good at one thing. It's good at AI. But there's a lot of other workloads that go along with AI, and those things need to be computed as well. So what we're looking for in kind of changing the game around this whole thing and making AI more affordable, which is going to unlock the next set of use cases for it, is to kind of put these smaller language models into CPUs, and then put the larger language models on accelerators, including GPUs. And if we can kind of provision racks that are built so that there is a mix of this, or maybe there's two racks sitting next to each other, one is optimized for small and one maybe is optimized for large. These are other alternative ways to approach it. Then we're going to be able to kind of utilize these small models to really drop the cost. And that's going to also get facilitated by virtualization. Why virtualization? Virtualization is the technology that allows us to partition resources. Partitioning resources is super important for AI because you want your AI to run predictably. This comes back to the cloud native architecture things that we were talking about earlier. In a cloud native architecture, like what Ampere builds, it actually allows you to provision containers on cores, and actually execute those models very, very predictably and for the lowest amount of cost. And the AI, or the virtualization comes in that you're addressing those needs for data security that we talked about earlier, or data sovereignty, all these sorts of things. Virtualization is a very mature technology on CPUs. So you can pack a lot of models onto one CPU if they're small. Now, of course, the big model is still going to have to go onto GPUs, but GPUs are really better at one model, and don't mess with it. That's how training was done. Stick a lot of batching into a large model, and that's going to be something that the GPU is going to be very, very good at. But guess what? It's not very good at being virtualized. And so that rigidity of that particular accelerator function makes it less flexible inherently, right? Is it bad? No, it's good, still good for the right job, but it makes it less flexible. And so we're blending these things, getting the small language models into containers, into virtual machines on CPUs is going to really drop this cost. We'll show you a little bit more about how much cost you can drop out of this. Next slide.
Yeah, so effectively you're doing right model, right infrastructure, right? It's no
Yep.
longer necessarily a one size fits all, right? Where you're putting, if you're doing AI or you're doing anything with AI, you put it here, right? What we're seeing is
Right.
kind of starting it's not commoditization yet or anything like that, obviously, but you're starting to see a little bit more piecemeal where you place stuff matters more, right? Very similar to what we've been doing in cloud for a decade, right?
Exactly, exactly. I think maybe the one difference is that where in the early days of the cloud, when we started to get into cloud native computing and what we called serverless, especially serverless programming, didn't really care about what you were running on. I think there's got to be a little bit more awareness, about what you're running on, especially to optimize for power. And this is something I was on a podcast the other day talking about this very subject, where coding has to get a little bit more intelligent about where it schedules things, especially if you're optimizing for cost and power. And I think you're gonna see that as a building area of energy and focus and innovation in the next 3 to 5 years, because of course, you know, uh, saving power is becoming a much more sort of imperative thing to do. It's not just kind of altruistic and kind of good for the environment and all the older reasons. It's also super imperative for economical reasons and also for conservation reasons, because power is going to be harder and harder to come by.
Well, yeah, a lot of the grid sustainability stuff, like it's not that everybody in the industry is a good human being that wants to save power, right? It's in a lot of cases you can't get power, right? You see
Yep.
in the news almost all the time somebody buys a bunch of land to build a data center and oops, they're not going to be able to get power there for 5 more years, right? So
Yep,
it's as much
exactly.
as we as much as we are all good people, hopefully as well, and consuming
Yep.
less energy is always a good thing even if you were
Yep.
a bad person, you can't right now, right? So that's where I think it's starting to get tricky.
Yes, I totally agree. Now, to put some numbers behind some of these things that we're talking about, Domin, I'm going to show you here kind of back to that perf per rack analogy, putting a bunch of AI into a rack that's specially built for small language models. Here is essentially a pro forma kind of economical picture for doing that. You have a rack that's got a budget like we talked about. It's got 12.5 kilowatt budget. This is sort of arbitrary on our part. We chose it for mostly reasons of kind of fitting these systems into a power budget. But you take that power budget and you see how many systems. In our case, if you're using Ampere 1M, you can choose, or you can actually put 17 systems into that power budget. If you're using some of the high volume optimized for inference GPUs today, you're going to be able to fit 4 of those systems. And if you're using a GPU system that's optimized for training, you're going to be able to fit 1 in that 12 kilowatt budget. Now, each of those systems has a certain amount of capacity for processing models. And what you're seeing on the left-hand side with Ampere 1M is our ability to densely pack those models into each CPU. So at a rack level, we could actually be processing 408 individual simultaneous models, and that is going to drop the cost, the operating cost per year radically. The operating costs in red on this chart are actually computed at 22 cents per kilowatt hour, which I think is pretty small if you take burden power in the world today. And burden power meaning you're going to be paying for the cooling and the concrete
Yeah.
and the all that stuff, right?
Right.
Um, and so but you can see quickly as that SLM goes up from 1 billion parameters to 8 billion parameters, that the number of models you can actually fit goes down really quickly. Actually, that's that exponential curve starting to come into play there. And so the cost starts to go up radically by actually doing that. On the right hand side of this chart, you're seeing essentially the effect of those GPUs not being virtualizable, or not very kind for virtualization. And so you're seeing an 8 GPU system, 4 of those meaning 32 GPUs in a rack of that budget, being able to essentially operate 32 simultaneous models. And then, of course, if you get up into a 70 billion parameter model with this particular GPU, then you've got to use 2 GPUs to actually compute that model. This is the exponential curve coming, and all of a
Yep.
sudden those costs go way up. Same thing all the way out on the far right, right? These are big GPUs, essentially not a very good decision for small models, right? I think this is intuitive.
Yeah.
Um, and so, essentially, I'm kind of backing up the premise of, if you really want to drop the cost of AI, then start to move the models down. It's not that
Mhm.
all tasks can be taken care of with small models, but if if you can if you can do this, and if you can get into mixtures of experts and things like that, then you're going to have a lot better luck, dropping the cost of the AI service.
Yeah, for sure. And the more you can, the more flexibility it gives you, period. Right. If
Yep,
you're there's no reason to do things on a massive model that can be done on a small one, right? It's the same reason
that's
that
right.
I don't drive a tank every day. It would be cool to drive a tank every day, but a car is just fine, right? I don't need tanks in most cases.
Yeah, you're getting into one of the guys on my team's got his favorite thing is car analogies, and he always gravitates to the, well, yeah, of course I'd like a Ferrari, but it's not going to necessarily be the right thing to drive my kids to school in.
Yeah. Yep, exactly. I was thinking like Deuce Deuce, like a six-wheel drive military Jeep, but same
Yeah,
thing. Yeah.
yeah. Good thing about car analogies is everybody's got their own sort of model in their head, and they can all
Yeah,
relate to
right.
it. Yeah.
Yeah.
All right, we're going to talk about systems really quickly to close this whole thing out,
Yep.
in terms of kind of the prepared material. But systems, okay, I want to come back to some things that we were talking about earlier. Everybody's going to have LLMs and SLMs, right? So one of the things to think about here is putting LLMs on accelerators, and those accelerators, of course, go into other regular servers. In many cases, there can be multiple, N accelerators in a CPU or server platform. But you can also schedule the small language models on those CPUs. So some kind of combination of those two things is probably the right blend for a lot of the future workloads where we've got kind of domain area models that need to be super um, large in size, but also kind of general experts. In other words, they know a little bit about a lot of things. Why? Because those types of models are going to be able to kind of guide into the smaller models. Take this question about Shakespeare and route it to the Shakespeare model, just to pick something.
Yeah.
So blended racks. This is something that we really want to see. But the problem is, next slide, is that these AI systems are actually skyrocketing in complexity and cost, right? You got more processing, more networking, more storage, higher thermal density, a lot of direct liquid cooling strategies being employed. In fact, if you go to any of the trade shows in the world today, what you're going to see is pretty much all the same racks from very different vendors. And they're all essentially, liquid cooled racks. And this is the state of the art for AI compute in the world today. The problem is that it's got a lot of vertical integration into it, and it's currently dominating, the AI industry in terms of a lot of different types of things that are required to actually build these racks. Everything from standards to the interoperability of components, to the actual systems providers that fabricate these things and manufacture them and get them into the marketplace. There's a lot of different complexity in this entire supply chain.
Well, I
So
think
next,
there's a lot of talk right now about standardization of that too, right? Of open
yes,
standards and things like that. Yeah.
yep, exactly. So one of the things that this complexity begets, obviously, is kind of more peripheral components, higher speed networking, more board layers, more power delivery, all these sorts of things, and that's also driving up cost. So the thing that we really want to kind of do is open this vertically oriented industry right now into a lot more horizontal industries, because then you're going to get the maximum innovation into this type of a market, and that's going to help, along with the competition, of course, classic economics, drive costs down.
Yep.
So at this time, this is a plug for OCP. Um, truth in everything, we're a diamond sponsor of the OCP, but so are a lot of other companies. So but OCP is in a really, really cool position right now because it has been doing open standards for exactly this kind of thing for probably over a decade now, a decade and a half, I would say, somewhere in that range. And yeah, part of that's gray beard is, you kind of start to lose some of the resolution, as to when things actually happened. Um, but uh, but so these standards are being built for the future of AI systems, and there's a lot of different kind of standards right now. The MHS set of standards, things like the DCSCM, which is what you see pictured here. This is an actual module for doing management, kind of rack management and server management, as in addition to the motherboards themselves, the systems themselves in modularity, being able to plug different, kind of mix and match components into the systems. And then, of course, now these accelerator blocks, these things that are going to be higher in power consumption, therefore harder to cool, but still a lot of need for these. This is where the LLMs are going to land. These things actually need to be standardized so that we can actually kind of have a lot more choice and a lot more innovation in the industry in a horizontal manner.
Yeah. Nope, that makes sense.
So here's kind of the host processor module. This is our particular Ampere 1M host processor module being provided by these particular suppliers, but this is really a plug for the HPM. Why? The host processor module is a very interesting kind of evolution of motherboards. What's really happened in the past is that uh, a CPU company such as ourselves or Intel or AMD or NVIDIA or anybody, puts out a processor, and they actually start to specify how to lay out a board and all of the critical components, which includes the memory subsystems, and to an ever increasing degree the I/O, right? The I/O subsystems, and they say don't deviate from this, because if you do, you're going to run into problems. But we had an industry that was built on building their own motherboards. Well, at this point in time, I think it's time to kind of dispense with that. Why? Because we're at the point with all that complexity I was talking about earlier of saying don't deviate from this particular design, and that's where the HPM comes in. This is a host processor module. So now the design is all done by the people that built the processor, and then of course that can be manufactured by a lot of different people. Um, but this kind of begets, because you can kind of plug a lot of the other things that are going to be the more differentiating pieces into this through standard interfaces like PCI Express and others that are also built on standards. So this is just kind of one of the hubs this type of standardization that's going to horizontalize the ecosystem.
Yeah, it's really interesting to see now, and maybe a good question for you just to pick your brain is why now? It seems like we're seeing more adoption of open standards than ever, right? So like
Mhm.
I've been in the industry a while, you've been in the industry a while. Used to feel much more monopolistic than it does now, but it feels like people are
Yeah.
starting to embrace the open standards concept. Is that do you feel like that is just a force of people asking for options when they don't have them? Like what do you think is actually causing that?
Yeah, I think it's two things. Essentially what you had. What actually this kind of comes back to some other industry dynamics that kind of were the kind of the precursor to OCP. What you had back in those days was a cloud market that was building data centers very, very densely. They needed a lot of equipment, essentially. And so they started looking at what was out there and available to them, and they said, geez, I don't want all of that stuff. I just need this stuff. And the subset of things that I need is much smaller than what you're providing, right? And
Yep.
that same dynamic started OCP. Now you see it happening again because now what we're seeing, even just in these slides, is I'm being asked for a super to be consuming these supersized, kind of systems, and I only need something that is maybe a fraction of that. Comes back to that kind of um,
Yep.
fragmentization, right, of the actual solutions. And so I think there's a lot of demand and interest in being able to break down the problem into smaller sizes so they can be fit across that entire span of markets that we were talking about earlier, right? Edge to cloud. And I
Yeah.
think these types of things are compelling for that. Now, the
Yeah.
final slide, I think this takes us out, is that it's not good enough to just stay with hardware standards. Now, we also need to be thinking about the software standards and the entire solution stack. So, Ampere and a bunch of our other sort of, kind of ecosystem partners have put together what we call the AI Platform Alliance. This is an organization now, 40 plus, I think it's almost to 50 now members and growing, of essentially providers on a bunch of different levels of the solution stack. Everything from the silicon itself, such as us and some of the accelerator providers on the outer ring of this diagram, to the ISVs and MSPs that are building stacks for AI to thread together, the hardware and the scheduling and the virtualization and all of the orchestration that goes with it with the actual end application, right? The use case, because that's what you really want to get out of this. Am I building a chatbot or am I building a language translator or am I building something with vision? All these different use cases. So the AI Alliance kind of comes in and supplies this kind of or not vertical, solution-oriented stack that kind of gives some guarantee of interoperability. So it kind of helps put all those modular pieces together on top of these standards that we're talking about. So if you're interested in joining us, there's the link to do so. And with that, I will pause and we can chat about whatever questions we'd like here.
Yeah, Laura, I don't know. Have we had any questions in the chat?
There are no questions at this time.
No questions at this time in the chat. Well, perfect. Do we want to talk? We've got basically a minute here. Is there anything else, Sean, that you wanted to talk about that was not in your PowerPoint? Anything else, tips or tricks? Obviously, as somebody who's been in the industry for a long time, head evangelist for Ampere, is there anything
Yeah.
that you want us to know about, that you want us to think about, or obviously, everybody listening as well? Just kind of a final sign off note.
Yeah, sure. I get asked of these kinds of questions, being an evangelist and in a lot of kind of panels and talk circuits and all these kind of things. And I think the one thing that I would like to, or my one wish for everyone who's trying to kind of cope with this AI wave, is to pause, take a breath, look at the options that are available, and then start asking questions, right? Because I think that in a hype cycle like we've seen, I haven't seen a hype cycle. I don't know about you, but I haven't seen a hype cycle like this since the .com, era.
Yeah.
And in these types of hype cycles, there's a lot of pressure, right, to get something done. Damn the torpedoes. I don't
Yep.
care what it
Move, move,
costs. All
move.
these sorts of pressures, right?
Yep.
And I just think this is a time to pause and really, really look at what it is that you're trying to do with AI, and then start with that use case, break it down. Like we were talking about earlier in those slides, break it down into smaller pieces, get some help. There's tons of help out there in the industry. And certainly don't just, like run headlong into, a lot of expensive infrastructure that you may have to kind of back out of later.
Nope, that's great. Appreciate that tip. You heard it from Sean first. Think first before you do. Measure twice, cut once. Right? Never a bad
Yeah,
ad.
exactly.
Yeah.
That's a great one.
Never as bad. Well, Sean, thank you
Yeah.
so much for joining. Thank you for taking time out of your day. Really appreciate you joining. All the insights that you've given us. I know you and I will be in touch plenty. Looking forward to that as well. But thanks for joining us for our summit. For everybody that's still keyed in right now, make sure you join us back here pretty shortly for our closing keynote from Mr. John White.
Thanks
See
for
you
having
there.
me, Dom.
Yeah, of course. Thanks.